We talked about that in the last section. Let's take a random rational expression. Something that we would have talked about to simplify. X squared plus 3x plus 2. And that's divided by x minus 3. How do we know it's a rational expression? Well, because it's got a numerator and a denominator. That means it's a function that can be written as a fraction. It's got some algebraic expression in the top and an algebraic expression in the bottom. And it's a fraction, so that means it's a rational expression. Now what we can do is we can take any rational expression we want and we can turn it into what we call a rational function, which is exactly the same thing as this, except we say that we'll make it a function of x. But it's going to be exactly the same thing. X squared plus 3x plus 2 over x minus 3. What does all this mean? It just means that any rational expression you have is a expression that has x's in it, right? Now we can take it and we can turn it into a function, which means, remember, a function takes input values of x, and then it calculates the output value, which is this calculation here, and then out pops the output value. So if you put input values of x in, you get output values, what we call f of x values out, and then that forms a pair of numbers that we can plot on a graph. So I can literally say x is equal to 0, calculate what the corresponding f of x value is. I can say x is equal to 1, calculate the corresponding f of 1 value, f of x, f of 1 value for the input value of 1. 2, 3, 4, -5, -6. I can calculate lots and lots of points and just plot them. It's exactly the same thing that we've been doing all along, just that these equations are a little more complicated because they're rational equations, rational functions, which means they can be written as a fraction like this. Now, the interesting thing is that these rational functions present a little bit of a problem, right? And most of you, I think a lot of you, can look at the function and see what the problem is right away. But in order to understand that there's a problem here, let's talk about an old function that we learned a long time ago. Let's talk about the function that's a line. Let's talk about something like 2x plus 3. This is the function. We know it's an equation of a line. How do we know that? Because it's mx plus b. Slope times x plus y-intercept. So you see, any value of x I put in here, any value at all, -10, -5, -22, and so on, I can stick it in here and out will come a nice number. It might be a negative number, it might be a positive number. But even if I put -10 million in here, it'll be 2 times -10 million plus 3, and I'll get a number. So for the line, right, the very simple function that we talked about a long time ago, any input value of x I put in there is going to be completely okay. In other words, I can calculate the output for any input that I put in there, right? So what we say when we talk about lines, because a line goes on and on forever in both directions, right? What we say is the domain, remember the domain, we talked about domain and range a long time ago. The domain of any function is what are the allowable input values of x that I can actually put into this function? Like, are they all allowed? Well, for the line, any value of x I want is completely and totally okay. So we say that the domain of this line is all values of x, all real numbers, all negative numbers, all positive numbers, all decimals, all fractions, anything out to plus and minus infinity is totally okay to put in here. So we say the domain of that function is all real numbers. But then when we start looking at rational functions, they always have a fraction bar, always. That's what the definition is. So it's always going to have a numerator and a denominator. And then you start asking yourself, don't even try to calculate it, just look at this thing and see, is there any particular value of x that's not going to work for that? Like, is there, and when I say not work, I don't mean if it's big or small. I mean, is there a value of x that I can't actually calculate the value of the output? Well, if you think about it, since I have a denominator here, if I put a value of 3 in for x, yes, of course I'll have 3 squared plus 3 times 3 plus 2. The numerator will be fine. But if I put 3 in for x, it'll be 3 minus 3, which will mean 0. And I'm going to divide by 0, which is going to cause a problem. So if I go and get a calculator and I divide by 0, it's going to say it's undefined, right? In calculus, we say when we divide by 0, it approaches infinity. But in truth, when you actually get to the point of dividing by nothing, dividing by 0, you can think of it as being infinity, but really the truth is when you divide by 0, it's incalculable. You cannot divide something by nothing because it technically can go an infinite number of times when you start thinking in terms of more advanced math. But from a point of view of what does division mean, if I take something and I start chopping it up into pieces, that's what division is. How can I chop something up into pieces when the width of each piece I'm looking for is 0, right? How can I do that? I can't do that. It's not possible. I can divide by 0.1, That's a small number. I can divide by 0.0001. I can divide by 0.000000001. But if I divide by 0, I can't do it because I'm dividing by nothing at all, right? So that means that this function has a big problem when x is equal to 3. It cannot be done. So because of that, the domain of this function is not all real numbers. This one had a domain of all real numbers. I can put anything I want in here, but I cannot put 3 into here, right? So basically, when I say because, things like, anything over 0 is undefined, what that means is that because of that, what I take is the denominator, I set the denominator equal to 0. That means when x is equal to 3, that is not in the domain of function. So if I were going to write down the domain of this function, right? If I were going to write down the domain of this function, the domain of function, it would be something like, usually put it in squiggly braces to kind of denote that it's a set like this. You could say all real numbers except x is equal to 3. And what it literally means is I can put any number I want into this guy, negative 2,000, negative 5,900, 0.55, positive 3,024 decimal 55672. I can put any number I want in, but I can't put 3 in, because if I put exactly 3 in, the whole thing becomes impossible to calculate. So the domain of this function basically arises when I look at the denominator and I set the denominator equal to 0, because that's going to give me the value of x that's not possible. So in this case, I set the denominator equal to 0. I solve it by moving 3 to the other side. X is equal to 3 is a problem, so I say the domain of this function is all real numbers except for 3. So when you're asked on a test, here's a rational function, tell me the domain. All you have to do is look at the denominator of the thing, set it equal to 0, calculate the problem values, the problem areas, or the problem numbers, in this case 3, and say the domain is everything except that, right? Now, look at our friendly line here. Technically, this is a rational expression also, of course. This is just this divided by 1, because anything can be divided by 1, right? So technically, even though it doesn't look like a rational expression, it is a rational function. It's just divided by 1. But there is no value of the variable in the bottom. It's just a constant. So setting the bottom equal to 0, 1 equals 0, it doesn't yield any values of x that cause this to be a problem. So because there are no problem values of x, we say that this is all real numbers is the domain of this guy. All right? So the domain, you set this denominator equal to 0. That's one thing you have to know for rational functions. What's the other thing you have to know? The other thing you have to know is if you look at the numerator, right? The numerator is this guy right here. Think about it. Any fraction, there are going to be problem values in the numerator also. They're not going to go to infinity like this, but they're going to be problem values. What happens if this numerator of this fraction ever becomes 0? Let's say, I can do anything I want. Let's pick just random fractions. What do you think the fraction 0 over 2 is equal to? Well, 0 divided by anything is 0, okay? What do you think the fraction 0 over 10 is equal to? Well, it's equal to 0. What do you think the fraction 0 over negative 5 is equal to? Well, it's 0. You see, the point is, anytime I have 0 divided by anything, it gives me 0. So you see, I know when this function goes to 0, right? Goes to 0, when f of x is 0, it always happens when the numerator is equal to 0. See, in this case, the numerator was 0 and it drove the function to 0. The numerator 0, it drives the fraction to 0. Numerator 0 drives the fraction to 0. Anytime this numerator goes to 0, it drives the whole thing to 0. So that's why the title of this function is called Domain and Zeros of Rational Functions. We've already learned how to find the domain. All we do is we set the denominator equal to 0 and we find those problem values that are not in the domain, right? To find the zeros of a function, that just means what places in the graph do the function actually go to 0? And to do that, all you do is you take the numerator of the fraction and set it equal to 0. So in this case, we have x squared plus 3x plus 2. We set that equal to 0. And we say, okay, whatever values of x make this whole thing go to 0, it's going to drive the function to 0 at that point. How do we find this? Well, we can factor it. We factor and solve. We've done this before. That's why we learned that skill already. X times x gives me x squared. 1 times 2 gives me 2. The only thing that works is plus and plus. So you see, when I multiply this out, I get exactly what I had before here. Now, what values of x actually make this thing go to 0? Well, this one means x is going to be equal to, let me do it properly instead of skipping steps. X plus 1 can be equal to 0. X plus 2 can also be equal to 0. So that means x can be, move this over -1, x over here can be equal to -2. What does this mean? This has absolutely nothing to do with the domain of the function, right? This is the zeros of the function. This means where does the graph cross the x-axis? It means where does it go to 0? You know, when you plot something, you have the x-axis and you have the f of x, the y-axis, right? So the function is going to do something, but at some values it's going to cross the x-axis, meaning it's going to go to 0. These are the values where it goes to 0 because these are the values that when substituted into this thing drive it to 0. I mean, look at -1. Put -1 here, square it, you'll get 1. Put -1 here, you'll get -3. -1 squared gives you +1. -3 will give you -2. -2 plus 2 gives you 0. So when you put the value of -1 in here, you get 0. Similarly, when you put a -2 in here and go through the calculation, you'll also get 0. So that means these guys are the zeros of the function f of x, right? So if I were going to circle something, I would circle the domain is like this, and the zeros of the function are this. So let me go over here and summarize really quickly. To find the domain, set the denominator equal to 0. Those are going to give you the problem values that are not in the domain. To find the zeros of the function, set the numerator equal to 0. This is really the punchline of the whole thing, right? When I set the numerator equal to 0, it's going to give me the values that are going to drive the whole fraction to 0. We call that the zeros of the polynomial. We also call it, you'll see there's a synonym for the word zeros of the rational function. We also call it the roots. So some books will call it the roots of the polynomial or the roots of the function. Some will call it the zeros of the function, but for this purpose it means the same exact thing. So if you see roots, it's the same thing as zeros, right? So I like to use the word zeros because it really describes what's happening. We're finding the values that drive the thing to 0, whereas for the domain, we're setting the denominator equal to 0. That's going to be the problem values that drive the whole thing to infinity, basically. Now, the purpose of this is not to graph these things, to learn how to graph rational functions, but I do want to graph or sketch this. And I've done this, you know, on a computer and just kind of look at what it looks like so I can show you what these things physically mean so you can get an actual picture in your mind. So this is not an exact graph, all right? But what we want to do is sketch it. I want to show you that it makes complete sense what zeros and what the domain of the function is. So this is x, and this is, we used to call it y, but now we call it f of x. These are the input values, these are the output values. Now what we're saying is that the domain of this function is all real numbers except for x is equal to 3. So what I'm going to do is I'm going to say, we're going to go, this is x equals 1, x equals 2, x equals 3. I'll go ahead and put a 3 right there. I guess I can put a 2 and a 1, whatever, it doesn't matter. But at this point, at x is equal to 3, it's a problem value. Because what did I say before? What I said was that when x goes to 3 here, the whole denominator goes to 0, and as you get closer and closer to 0 on either direction, it drives the entire fraction larger and larger. You know, when you divide by 1, we all know how to divide by 1, but when we divide by 0.5, and then again if we do it again at 0.1, if we divide by 0.001, if we divide by 0.00001, and so on, as we divide by smaller and smaller numbers, the calculation of the fraction gets really, really big. If you take 5 and divide it by 0.000000007 or something like that, you're going to get a really big number because you're dividing by something small, right? So as you get very close to this value of 3, the function blows up to infinity. So what we do is we put a dotted line here to show that this is going to be a problem point. Now I'll come back to that in a minute. Then we have the zeros of the function. This is where we set the numerator equal to 0. The values of interest here are, and I'll go ahead and, I guess I'll do it here, -1 and -2. So here's -1. Let me think how I'm going to draw this. Let's put this -1, and then here will be -2. Okay? And what we know is that at this value, this function must go to 0. So I'm going to put a dot on there. And at this value of x is equal to -1, the function also goes to 0. So what we have here is a situation where at this point, the function actually crosses the x-axis because f of x is 0 at this point. And also at this point, the function crosses the x-axis here because f of x is 0 also at this point. But as we get closer to this dotted line, the function blows up to infinity. Or it might blow up to negative infinity, depending on how you're approaching it. But if you were to plot this on the computer, what you would see is something like this. And this is not an exact graph, so please don't get upset if it's not exact. But basically what's going to happen is the function is going to come in like this. It's going to cross, but it's going to go immediately back down, and then it's going to bend over and go really, really far down as we get closer and closer and closer and closer to negative infinity. And then on the other side, you're going to have another part of the function that approaches this dotted line, but then kind of flies off this direction. So you see you have it coming in. This is not smooth. I'm sorry about that, but it comes in, bends over, goes through both of these points, and then flies down to negative infinity. And then up here, it gets to positive infinity. Why is it negative and positive infinity? Because when you're on this side, when you're just on this side of 3, like negative 2.99999, you have negative 2.9999999. I'm sorry, not negative. It'll be just 2.9999, right? So 2.99999 or something like this minus 3 will give you a negative number, a really small negative number. When you divide by a really small negative number, it's going to blow to negative infinity. But on this side, you're going to be just on the other side of 3, 3.00001. When you put 3.00001 here, minus 3, you'll get a really small positive number. You divide by a really small positive number, you're going to get a really large number approaching positive infinity. So when we call these vertical dotted lines, we call them vertical asymptotes. That means the function never really gets to that dotted line, but it gets off to infinity or negative infinity as you approach that dotted line. So we're going to graph rational functions a lot more later. I'm just sketching this for you now. What I really want you to pull out of it is that all of these zeros in domain make perfect sense. The domain is all real numbers except where x is equal to 3, because I can go out to negative infinity and choose any number I want to put into this function except for the one right here. The function's not defined here, so x is equal to 3 is not in the domain. That's what that tells me. Over here, the zeros of the function are just the two places where the function crossed the x-axis, because that's where the function's 0, and you can see it pops up over and goes right down. If you were to graph it, that's pretty close to what you would get. The takeaway from this is to find the domain, set the denominator to 0. To find the zeros, you set the numerator equal to 0. Now we're going to do one more of these. We want to find the domain, and we want to find the zeros of the function f of t equals t squared minus 9 over t squared minus 9 times t. So now that we've got the theory out of the way, I want to be able to apply it to a kind of a complicated looking function. I mean, I don't know what this looks like. Do you? I have no idea. I'm not a computer. I've actually graphed it so that I could see what it looks like. But even without graphing anything, I want you to be able to tell me what are the zeros of the function and what is the domain of this function. So to find the zeros, how do we find the zeros? The zeros are basically, where does this function go to 0? Where does it cross the x-axis? We just take the numerator, t squared minus 9, and we set it equal to 0, because when the numerator is equal to 0, it drives the whole thing to 0. So we have to solve this equation. So we know we can factor this because this is the difference of two squares. If you don't believe me, write this as 3 squared. Difference of two squares will be t plus 3, t minus 3, equals 0. And that means either one of these can be equal to 0. Which means that, whoops, I meant to do this, t plus 3 equals 0. So that means when I move it over, t can be minus 3, or t can be positive 3. So you see, there are actually two values that drive this rational function to 0. Those two values are these two values. So these are the zeros of f of x. So on your exam, without graphing anything, if I just said, hey, what are the zeros of f of x, you would circle it. You would say there are two values that drive this function to 0. And you can see, if you put the value of 3 in here, 3 squared is 9, 9 minus 9, 0. It drives the whole function to 0. Negative 3 goes in here, you square that, you also get 9, 9 minus 9, 0, drives the whole thing to 0. These are the zeros. I said f of x, you all know that it's a function of t, sorry about that. But that's the zeros. All right, now how do I find the domain? So to figure out the domain of this function, what do? We set the denominator equal to 0 because those are going to be they're going to be the values of t that aren't even allowed to go into this function because they blow the whole function up to infinity. So we say t squared minus 9 times t is equal to 0. And we have to solve this equation. So we can pull out a t. Inside we'll have t minus 9 equal to 0. So we have t can be equal to 0, and this can also be equal to 0. So we have t is equal to 0, and also t minus 9 can equal 0, which means that t can be equal to 9. So what it means is that two different values of t cause problems for this function. So the domain is all real numbers. That means all negative and positive numbers except for t equals 0 and t is equal to 9. This is what you would circle for the domain. All real numbers except for t is equal to 0 and t is equal to 9. Why? Because if I put 0 in here, what happens? 0 squared is 0, minus 9 times 0 is 0. That means the whole thing goes to 0. You divide by 0, it's not allowed, it's undefined, or goes to infinity. If I put 9 in here, 9 squared is 81, minus 9 times 9 is 81. Again, I get 0. It does exactly the same, has exactly the same problem. So it's a little different because in the previous function, there was only one problem value in the domain. Only one, because there was only a very simple thing in the bottom here. But this one actually has two different problem areas in the denominator that those are the undefined, unallowed values of t because they drive the whole thing up. And they're also, again, two zeros. Now this function is really weird looking. I'm going to sketch it for you, not because I expect you to know it, but because I was curious and I want to share it with you because it's kind of interesting. But I want you to mostly understand what this stuff means, so I'm going to sketch it for you real quick. So what we have is a y-axis, or an f of x axis is what we really call it. So we have x, and we have f of x. And again, don't get upset. This is not going to be exact by any stretch, but it'll be good enough to give us some idea. So what we want to do is draw some tick marks here. What do we draw? Let's draw -1, -2, -3. So this is going to be -3. Why did I stop at -3? Because I know I have a 0 of this function at -3. And I called it x, and again, I'm sorry about that. So this is t, and this is f of t, right? But at -3, I have a problem because it's not really a problem. It's just that it's a 0 of the function. The function goes to 0 here, so I know the function is going to actually cross the x-axis at that point. I also know that the function is going to cross the x value, or the x-axis, also at +3. So I'm going to go ahead and write this right there. So I have two known points of the function just because I've solved for the zeros of the function. They have to cross. It has to cross there. But I have two problem areas. One is at 0, one is at t is equal to 9. So let's keep going. 4, 5, 6, 7, 8, 9. And I'm going to go ahead and put 9 right here. And I'm going to put a dotted line because that's going to be a vertical asymptote. Why do I know it's a vertical asymptote? Because at 9, the function is going to blow up to either positive or negative infinity. And so it's never going to reach this dotted line, but it's going to get infinitely close to the dotted line. So you just put a vertical line there. So at 9, there's one of those asymptotes. Also at t is equal to 0, which means right on top of this. So just to make it clear, I'm just going to put a little dotted line kind of right next to this, but really it's directly on top. This is another vertical asymptote. So here's the million-dollar question. What does this actually look like? And it's really weird. What happens is the function is going to come in from the left, and then it's going to go down like this to negative infinity. Then the function, because again, this is an asymptote, it has to start close to here at positive infinity. It's going to come down, it's going to snake over through this, and then it's going to bend all the way over and get infinitely close to that line, but it's never going to touch that line. And then over here, I'm going to have another portion of the function close to this, which is just going to kind of end up doing something like that. All right. This is graphed in a graphing calculator or a computer. I just did it mostly to explain what's going on here. So this is an example of a very complicated rational function. The function goes through two zeros. We call them zeros. You also can call them roots, -3 and +3. We calculated them, and that's where they're at. The function only crosses the axis there. And there are two problem areas in the domain where the function isn't even defined at all, at 0 and at 9, so we put dotted lines there. At these values, notice the function doesn't even go through this dotted line. You can think of the dotted line as like the speed of light. It's like a barrier. Nobody can go faster than the speed of light, right? So through the vertical asymptote, the function cannot penetrate it, but it can get infinitely close. And actually, even though I brought up the speed of light, when you learn physics, it's exactly the same kind of thing. The speed of light barrier ends up being like a rational function like this, where your speed can never get past that vertical line. The equation in relativity theory that talks about that actually is a rational function, right? So anyway, and the function cannot go through that, but it can get infinitely close to that in both cases. Over here, it can get infinitely close, infinitely close. So I don't want you to be able to reconstruct this on your own. I did it using a computer, but basically if you just stick values in for t and just keep on going and then get the points and plot the values, this is what it will look like. The point of this function is not to get bogged down in graphs, but I did want to sketch a couple of graphs just to show you what a domain of a function looks like, what a vertical asymptote looks like, and what a zero of the function looks like. Zero is where it crosses and so on. In the next lesson, we're going to continue finding the domain and zeros of rational functions, but we won't graph those. I just want you to do the calculations to figure out what the zeros are and what the domain is. And then after we do that next lesson, we will then graph rational functions where we'll roll up our sleeves a little bit more detailed and really learn how to sketch these things without using a computer or any other device like this, just using graph paper. So follow me on to the next lesson. We'll continue working with domain and zeros of rational functions. Learn anything at mathandscience.com.